Welcome back, guys, to my sixth video. My previous 5 videos have been uploaded on my channel, so do go check it out. Today's video is again based on polynomials as mentioned in the schedule. I will be first completing polynomials, then moving to the next chapter. Completing polynomials basically means I will be going through various types of questions and concepts, explaining them in depth with the proofs and all. Today's concept is basically very, what should I say? Very important concept, rational root theorem. From here comes its corollary, which is the integer root theorem. So today we are here with rational root theorem. This is a very important one. Do check out the proof of it, which I am going to show up here. Important theorem regarding the rational roots of polynomial equations. This rational, its corollary is integer root theorem. What are we given here? We are given a polynomial equation, which is the basic polynomial equation, the general form, which is your a n x to the power n plus a n minus 1 x to the power n minus 1 plus a n minus 2 x to the power n minus 2 plus a1x plus a0 is equals to 0. This is my equation, basic equation. We are given that a rational number p by q. So rational number p by q, where basically as fractions are defined or rational numbers are defined, q shouldn't be equal to 0 and GCD of p comma q should be 1. That is, they must be co-primes, that is prime to each other. Example 3 and 4, 2 and 7, like this. So what are we given? That is a root of the equation, this, where a0, a1, a2 all are integers. That is my a0, a1, an is an element of z, which is my set of integers, and my leading coefficient shouldn't be equal to 0. Then what is given? P is a divisor of a0 and q is a divisor of an. Basically, this proof claims that if p by q is a rational number and is a root of the general polynomial equation, then p has to be a divisor of a0, that is the constant term, and q has to be a divisor of an, that is the leading coefficient. Now comes the proof, that how is it possible? We are claiming. Now I will be showing you the proof. This is the main agenda today, to know how the proof is done so that we can apply it from the scratch. I'm changing the color. I think it looks well with orange. Yeah. So what is my equation? A n x to the power n plus a n minus 1 x to the power n minus 1 plus a n minus 2 x to the power n minus 2 plus a1x plus a0 equal to 0. Since we have p by q as a root basically means it is that value of x for which the whole equation adds up to 0. So basically I can put p by q in place of x. So an into p by q whole to the power n plus a n minus 1 into p by q whole to the power n minus 1 plus a n minus 2 into p by q whole to the power n minus 2 plus dots a1 into p by q plus a0 equal to 0. I'll be simplifying this. How? I will be separating the terms out here. This a n into p to the power n by q to the power n plus a n minus 1 into p to the power n minus 1 by q to the power n minus 1 plus a n minus 2 into p to the power n minus 2 by q to the power n minus 2 plus dot 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 a1 into p by q plus a0 is equal to 0. My next step would be to multiply q to the power n to all the terms. Basically a n into p to the power n plus a n minus 1 into p to the power n minus 1. Now since I multiply q to the power n to all the terms, it will be basically here in the second term it will be q to the power n by q to the power n minus 1, which is your q to the power n minus of n plus 1, which is your q to the power 1, which is q plus a n minus 2 into p to the power n minus 2 into q square plus dot 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 a1 into p into q to the power n minus 1 plus a0 into q to the power n equals 0. My next step would be to simplify again. Now how am I going to simplify? Here we need to take a good look at the equation, that is the expression. How will my things follow up? I have a n into p to the power n. Just a second, guys. Some problems with my internet. Yeah, we are good, I guess. Yeah. A n into p to the power n plus a n minus 1 into p to the power n minus 1 into q plus a n minus 2 into p to the power n minus 2 into q square plus dot 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 plus a1 into p into q to the power n minus 1 plus a0 into q to the power n is equals to 0. Now what am I going to do? That is a n minus 1 into p to the power n minus 1 into q plus a n minus 2 into p to the power n minus 2 into q square plus dot 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 a, this is my a 1 into p into q to the power n minus 1 plus a0 into qn. This is my q to the power n. Okay, this is a slight mistake. Q to the power n, this is not a suffix. This is basically your minus a n p to the power n, because I'm taking this a n p to the power n to the right hand side. Then what will be left with is this. What am I going to do? I am going to take this q to the right hand side. What am I left with? A n minus 1 into p to the power n minus 1 plus a n minus 2 into p to the power n minus 2 into q. I am left with 1 q, it's q square, 1 q goes to the other side and 1 q is left here, plus dot 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 plus a1 p into q to the power, this is your n minus 2 plus a0 into q to the power n minus 1 is basically your minus an p to the power n by, this is my q. Now, one very important observation. What is my observation? I have claimed before that a1, a2 up till an, they all are integers. So integer multiplied by any number is basically integer. So my an minus 1, an minus 2. So basically any linear combination of an minus 1, an minus 2 up till a0, their summation is going to give me an integer. Which means my LHS is belonging to Z. And what have I claimed? Q doesn't divide P. Since they are co-primes, then it will be basically Q doesn't divide any power of P. That means here only one case is possible, that is Q divides AN. For this whole thing to be a logical integer. Okay, we are good with this. Again, for my next step, I will be changing the color. Let's do it with red. I have shown one part that Q divides A, and now I need to show that P divides A naught. Okay. So AN into P to the power N plus A N minus 1 into Q P to the power N minus 1 plus A N minus 2 into Q square P to the power N minus 2 plus dot dot dot. I am writing the same equation, okay? A1 into Q to the power N minus 1 into P is equals to, I'm going to take my A0 term to the RHS, that gives me minus A0 into Q to the power N. Okay, yep. So now what can I do is I'll be taking 1P from the LHS and divide it in the RHS. How? If I take 1P from here, I'm left with AN into P to the power N minus 1 plus AN minus 1 into Q into P to the power N minus 2 plus AN minus 2 into Q square P to the power N minus 3 plus dot 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 A1 Q to the power N minus 1 is equals to minus A0 Q to the power N by, what will be left with here is my P. Since I have taken 1P from the LHS and put it in the RHS. Again, same observations. I have claimed that my AN minus 1 up till A1 and A0, they all are integers. So any linear combination of them and the summation is going to be an integer. So basically I have pulled 1P from the RHS, from the LHS, and brought it back to my RHS, that is divided it in the RHS. I'm left with a fraction that is a rational number in the RHS. But I know that my LHS is going to be an integer, that is my LHS is going to be an integer, and we have again claimed that P doesn't divide Q. That means my P won't be dividing any higher power of Q. That simply means for this quantity to be an integer, that is an element of Z, my p must divide a to the power, sorry, not power, a is 0. These are my two claims which I had done. That is, p is a divisor of a naught. That is, your p divides a is 0 and q divides a n. That is, q divides a n. So these were my two claims and I have successfully claimed it. So whenever a rational number is a root of a general polynomial equation, may it be of any degree, may it be of 1 degree, 2 degree, 3 degree, or any degree of nth degree 2, and if my p by q, that is a rational number where q is not equal to 0 and my GCD of p and q is 1, is a root of the general equation, then we must always remember that the denominator, that is the q, is going to divide the coefficient of the highest degree term, and my p, which is in the numerator, is going to divide the constant term in the polynomial. So this was the rational root theorem. From here comes the corollary. That is the integer root theorem. Which tells me that if the term q is not there, that is my denominator is not there, if we have only p, then p is always going to belong to an integer group, then p must divide the constant term. That is, p will be dividing a naught. This is true for any p belonging to z. This is my corollary, that is my integer root theorem. Okay. Now my usage. What are the usages of this rational root theorem? Many a times we are given some big, probably quadratic equation or cubic equations whose roots we need to find in certain cases, and the problem which we need to deal with is it's a huge equation, a very complex equation. Probably some roots would be very hard to find. In those cases, my rational root theorem and my integer root theorem comes to play. What we need to do? We simply need to find out divisors of the constant term in the polynomial, of the constant term of the polynomial. This is the first step we need to take for finding out roots. We take this step, we find out the divisors, we just put them in place of x, and my answer is going to come out very easily. We don't need to work tirelessly for finding out the roots of the equation, because this would be taking a whole lot of time, which could be devoted to other aspects of the problem. So this was it for today. My rational root theorem, a very important theorem, various usages. I would be referring the book Pathfinder for Olympiad Mathematics, which is a very good book for Olympiads that can be used as a guidebook by you guys who are preparing for Olympiads or for ISI, CMI and any other mathematical related competitive exams. Do go through it. Do go through the examples of rational root theorem and the integer root theorem. They are given at a very good level. Some advanced questions are also there. And in my next video, I will be probably coming up with some interesting questions related to rational root theorem, which will be testing us out the importance of rational root theorem. So that's it for today, guys. Do like, share and subscribe, and refer it to your friends who want to have a brilliant career in mathematics in future. Goodbye.